script, and we are now going to do chapter 3B. So if you don't have them out, please pull out your notes. If you didn't, for some reason, if you lost them, you can always print them from the Google Student Drive. So the Google Student Drive, the notes are there. I verified it. All right, this is a pretty easy section. So we're going to cover accuracy and precision. So accuracy is a measurement of an instrument is a numeric evaluation of how close it is. So the accuracy of a measurement or instrument is the numeric evaluation of how close the measured value is to the actual or accepted value. So accuracy is how close it is to the real thing. So which is more accurate? You have to think about more accurate here, not perfectly accurate, but closer to accurate. A football field is 50 yards, 75 yards, 95 yards, or 155 yards. Well, a football field is 50 yards is definitely too small. And so the closest one out of these four, I think, is 95 yards. Because it is more than 100 yards, but it's less than 155, and it's more than 75. So this is the closest value, so the most accurate measurement. Now, percent error shows you how close your experimental value is to the actual value. This is a formula that you will get very familiar with. You won't have to memorize it, but you need to know it. Eventually, you may memorize it anyway. Percent error, and sometimes I write that as just percent E, is the actual minus the experimental. Now, for actual, I also might use theoretical, and if I did, I'd put a T. The actual minus the experimental divided by the actual or theoretical value. The reason I say theoretical is because the theoretical value is going to always be the perfect world value, and that perfect world value is like if you do math. That's the math, what you would expect if you with the math. You do the math, you come up with a number and say, in a perfect world, that's what you get. But when you do the experiment, it doesn't work that way. Notice that the absolute value sign makes the percent error negative. Never negative, rather. Never negative. So percent error is always 0% would be the lowest percent error, and otherwise it goes up from there. So let's do an example. You measure the mass of a product of a chemical reaction to be 3.80 grams. According to your theoretical calculation. So you thought when you did the math, you should have come up with 3.92 grams. So this is the theoretical value according to your math. This is the experimental value. Okay, even though it says the mass of the product in the reaction, this is what happened when you did the actual reaction. So that's experimental value. So what's percent error? So here's the procedure. You write percent error equals theoretical minus experimental over theoretical times 100. You must write that. This right here with no values substituted is 1 point. If you substitute the values, that is not what I'm asking. I'm asking you to write the formula. Now you substitute the values. So percent error would equal the absolute value of, what's the theoretical amount? 3.92 grams minus the experimental amount, 3.80 grams, divided by the theoretical amount, 3.92 grams times 100. So now I've substituted the values. This is not the point. This is the point. Now we're going to do the math. I'm going to pull this up. Okay. And there we go. 3.92 minus 3.8 is 0.12. And so what I normally do is I cross out the top, put 0.12 grams, because grams minus grams is still grams. And this happens to be the correct significant figures for this math, but we're going to learn sig figs in equations like in the next section. So you will be required to use significant figures as soon as I've taught them. We're really close. So now that I have the value that I just divide by 3.92 and multiplied by 100. So I'm going to turn this back on. So I've already got the value 0.12, divide by 3.92 and then times 100, and it's 3.06%. Okay, 3.06%. And as far as significant figures goes, this probably has one more significant figure than I need. So it'd be 3.1% because this value only has 2 sig figs. But like I said, you haven't gotten there yet, but this is the sig fig answer. And I'll put SF for sig fig answer. Notice that the unit is percentage, and that's because when you do this math, now you have a gram on the numerator and a gram on the denominator, and they go ahead and cancel out. So it is just a percentage. It's an easy calculation. The hardest part is making sure you get the correct theoretical amount on the bottom. Okay, because whatever you divide by will make the difference in this equation. I always like to mark up my questions by putting experimental or theoretical when I'm looking at it and reading it to make sure I put it into the right spot. All right, now let's move forward with precision. Now before that, I'm going to give you a problem. So let's do a problem here on Edpuzzle. And I'm going to assume it's done. So now we're going to move on. Precision. How repeatable a measurement is, or how exactly one can make a measurement. So precision is two things. Do I keep getting it? That means I'm very precise. Or am I getting it to a smaller and smaller and smaller decimal place, or a smaller and smaller and smaller place value? Precision has to do with place value. Decimal places or place value. So write that in your notes. So if I look at these, the one that has the most decimal places is this one, so that would be the most precise. Now if I imagined having the number 10, 100, 101, none of those have decimals, but which one goes down to the lowest place value? Well, this one does. So this would be the most precise. This one really only goes to the tens, and that one really only goes to the hundreds. And like I said, we will understand that a little bit better as we move forward. So we're looking at most of the time it's the more the decimal places they have, the more precise it is, because we're going to be dealing with all kinds of decimals. Now you have this graphic in your notes to help you see that this first graph is kind of, think about the target here as what you're shooting for. It's not accurate and not precise. And if I kind of take an average of these by crossing them out, you can see that that's where the average would land, somewhere in there. It's not near the bullseye. Now this one is accurate but not precise. Well, it doesn't look accurate because accurate is how close it is to the real value. But if you take an average by drawing these, you can see that it lands inside the bullseye. So it is accurate, but it's not precise because all the values are all the way around. This third one is not accurate, but it's precise. Well, remember, precision is how repeatable. These are very repeatable values. This is like doing a math problem and getting the same answer over and over again, even though it's the wrong answer. You keep getting the wrong answer. You may have been precise, but you're not correct. And this one is both accurate and precise, and that's easy to see. The average is right in the middle of the bullseye. Okay? That brings us to significant digits, and this is where we really need to pay close attention, but we have a fun way of learning it, and it's pretty easy. The hard part is keeping up with the rules as you move forward in your calculations, but you get to use a reference sheet, and I have one on significant digits that you can print out and keep in your reference sheets at all times. Significant digits are those that we know for sure, and you have one estimated digit. It's always going to be one more than what you actually read. You can look in your textbook to see the significant digit work in your textbook, but you can also look at the significant digit handout, which, like I said, you can always use. Keep this handout to use while completing all homework assignments and quizzes and tests. All right, before I move on to what it is, let's draw a picture. If let's see, here we go. I'm going to draw this, and I'm going to mark this as 10, 20, 30, 40, 50, and these are all milliliters. Okay, I'm going to put a liquid in this container, this test tube, and it goes up to here. Okay, now if I was going to write down this measurement, I could say for sure that this goes to 10. So I could write 10. But I need to figure out, like, what is It only goes to the tens place. The ones place would be all these in the middle, but there's no ones marking. So this is about halfway between. So I'd put halfway between, so 15. 15 milliliters would be my correct significant figure value for this. Because I could look at this and say, well, maybe it's 16 milliliters because it's kind of a little bit higher. Or maybe I thought it was 14 milliliters. All of these would be correct values because they're all showing you what we know for sure, which is the 1. We know it's at least 10. And then they all show you one more place that we estimated. The 6, the 4, or the 5, the 6, or the 4 were all the estimated values. So the last significant digit is always the estimated significant digit. The estimated one is the last digit in the number, okay? All right. Now, some things to remember about significant digits. Leading zeros are losers, and I will, put my, I'm going to draw a little face here. All right, leading zeros are losers. I usually hold up my hand and make an L with my hand on my forehead to say that. And this is supposed to be my hand. I am not an artist, but leading zeros are losers. Decimal points make zeros count, and I highlighted and bold-faced the T's to help you to think about that. And then we're going to do the Atlantic Pacific rule. Okay, let's draw the Atlantic Pacific rule. And then we're going to watch a video about the Atlantic Pacific rule. So here we go. You need to draw this in your notes. This is the United States. And over here is the Atlantic. And over here is the Pacific. Okay? Now, how does it work? Well, I have a number like 1.08. And for the Pacific, that means present. That the decimal point, the point is present. For the Atlantic, it's absent. The decimal point is absent. Well, in this case, the decimal point is present. You can see it. So when it's present, you're going to come in from the Pacific. So you come in from the left. The first time you hit a non-zero number, you start counting significant digits. So this has 1, 2, 3 significant digits. Easy breezy. 3 sig figs. Okay, let's write another one. 20.005. Well, the decimal point is present, so I come in from the Pacific and I count 1, 2, 3, 4, 5 sig figs. 5 of them. All right, let's write another one. 0.07180. And all of these, by the way, significant digits can only happen if you have a unit. You need to know this. Sig figs must have a unit. Because why? It's a measured thing, and measurements have to have units. So it's always a measured value. So make sure you write that in there. I was trying to find a place where I put it in the notes. But all right, so let's look at this one. It does have a decimal point, so I come in from the Pacific. All right, I go through all the non-zero numbers, and I hit I go through all the zeros until I hit a non-zero number. There's the first one, and then I stop. And now I count 1, 2, 3, 4. 4 sig figs. So I hope you understand that one. Now let's do some that would be from the other direction. Let's say I have 202,000. And I'm going to put a unit because these are supposed to have units. I'll make all these grams. They have to have a unit. What do they have to have? A unit. What do sig figs need to be significant figures? A unit. Okay. So here I look. There's no decimal. The decimal's not there. So when there's no decimal, you come from the Atlantic and you go through all the zeros until you hit a non-zero number, and then you count. This one has 1, 2, 3 sig figs. Let's try another one. Sorry. I must be moving on to the next page. Yeah. So I'll put it over here. Let's see. 1, 5, 8, 0, 0, 0, 0.00007. Okay? All right. And I'm going to make it milliliters so that there's a unit. There's no decimal point, so the point is absent. So you come in from Atlantic, you hit the first non-zero number. Oh, the 7 is not a 0. So everything else counts from then on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sig figs. That's how easy this is. If you just learn the Atlantic Pacific rule, you will be able to determine the number of significant digits in everything, but it must have a unit, and it cannot be something you count like people or eggs, because counting things has infinite significance. It's not a measure. People are not a measurement. Eggs are not a measurement. They're things, objects that you count. So here's that Atlantic Pacific rule again, and this would be what's in your notes. And this helps you to see. Here you come in from the Atlantic, 1, 2, 3. Count. You'd go through the zeros. Here you come in from the Pacific. You hit a non-zero number. 1, 2, 3, 4 sig figs. Okay. All right. Let's move on. So before we do this, I'm going to go back to the Prezi, and we're going to watch the little video about this. Here's the video on it.
Skills that you need to have first. So the first thing you need to be able to do is you need to be able to look at a measurement and identify which digits in that measurement are significant and which digits are not. And remember, in a measurement, a digit is significant if it is the digit that is certain or the first guessed digit. So let's say, for example, I was reading this graduated cylinder, and we would look at that and say, okay, well, 36.5 milliliters. The 3 and the 6 were sure of. The 5 we're guessing at. So those two are certain. The 5 is a guess digit, but all of those digits are significant because I either know what they are for sure or have a really good idea of what they are. So this particular measurement here's got 3 digits. All are significant, so it has what we call 3 sig figs. Now, some cases, identifying the number of sig figs is very, very easy. If the number does not have any zeros in it, then life is easy because all non-zero digits are significant. So if my balance said this 65.346 grams, there's 6 digits in that reading. All of them are significant. 5 digits, so that means that measurement there has 5 sig figs. Zeros are the troublemakers, and the reason why is because sometimes a zero is a part of the measurement. When we say, yes, this digit here, this measurement is a zero. But other times, zeros are simply placeholders. For example, let's pretend that we were looking at Beaver Stadium here at Penn State. Now we know that there's 106,572 seats. So we might want to estimate, okay, how many people are at this game in this picture. And we can look at it and see, well, I know there's 106,572 seats. And man, it looks like those are all pretty filled. I don't see very many empty seats. So we might come up with a reasonable answer that I think there's 105,000 people in this stadium in this picture. And that's a pretty reasonable answer. Now, in that answer there, we can be pretty sure about the one there. It's definitely very close to full. We know it's not 90,000. It certainly can't be 110,000. So we're certain of both the 1 and the 0. And we're saying, well, it's awful darn close to full. So we're guessing at that 5. It certainly could be 104,000. It might even be 106,000. It might be 103, 104. We're guessing at the digit. We have a pretty good idea what it is, though. Now, in this case, we have the 3 zeros on the right side. We have no idea what digit should go there, so those are not significant zero. Those are merely placeholding zeros. They're there to keep the number that big. We're talking about 100-some thousand, so I have to have those zeros so that it's still 100-some thousand. So in that particular estimate, that measurement there, we really only have 3 sig figs. Again, that's a good example because the 3 zeros on the end are not significant zeros, but that 0 in the middle is. It is a part of the measurement. So with zeros, sometimes it's pretty easy. Whenever you have a 0 that is sandwiched between any 2 non-zero digits, those zeros are always going to be significant. For example, in this case, the zeros are sandwiched, they are significant. So we've are sandwiched between the 6 and the 3. So those two zeros surrounding the 5, those are significant. The two zeros on the end are not. So that digit has 5 sig figs. Now, a quick and easy way to tell if a zero is going to be significant, if you're not sure if it's just a placeholder zero or not, is to use what's called the Atlantic Pacific rule. This can help you determine not only if a zero is significant or not, but how many total sig figs the number has. So step number 1 is to imagine the number superimposed over the United States, and then ask yourself, does the number have a decimal? Now, before you ask yourself that question, you need to know a little geography to use the Atlantic Pacific rule. So you need to know which side of the U.S. the Atlantic Ocean and which side of the Pacific Ocean. There's a little help for you just to visualize again. Now, once you've done that, you need to ask yourself, does my measurement have a decimal in it or not? Now, of course, there's going to be one of two answers. If the answer is yes, and if a decimal is present, then you want to start from the Pacific side of the number. So imagine you're on the Pacific Ocean and you're cruising through the United States. You're cruising across that number. Well, you're going to cruise through all the zeros and you're going to keep going until you hit a non-zero digit. In this case, I hit the 4. When you hit a non-zero digit, that's going to stop you. Stop. Those are not significant zeros. Those are just placeholding zeros. In this case, they're just there to keep the number that small. Now, from the point you were stopped and for the rest of the digits over, those are significant digits. So all those digits at the end there are significant. So this particular number that we had in this example, we had 5 sig figs. Decimal was present, came from the Pacific side, the 4 stopped us, everything from that point over is significant. Let's look at another example. Now here I look at my number here over the United States and I ask myself the question, is a decimal present? In this case the answer is no. A decimal is absent. So this time we're going to do the same thing, but we're going to start from the Atlantic side. Again, we're going to cruise across, cruise through our number until we get stopped by a non-zero digit. In this case, the 3 stops me. So just like before, the zeros that we cruise through, those are not significant. They're just simply placeholding zeros. So from the 3 on, all the rest of those numbers are significant. So that number there had 3 sig figs.
All right, so that's the end of that, and you can, I might put that on Edpuzzle in a separate place for you to look at. So that brings us to this. So how many significant digits are in the following? Okay, so I'm going to do the first one with you. I'm going to keep following the Atlantic Pacific rule. So it's present, so it comes from the Pacific. So 1, 2, 3, 4, 4 sig figs. We have a unit, that's important. Must have a unit, must have unit. It's absent. I come in from the Atlantic. This one only has 2 sig figs. It has a unit. It's present. I come from the Pacific. 1, 2, 3, 4, 5 sig figs. Cookies is not a unit, so this is not applicable. Not a unit. All right. This is make sure we differentiate between the number and the letter here, but a decimal, seconds is the unit. It's present, so I come from the Pacific. Only 1 sig fig. All of these guys are placeholders. Placeholders. All right. This one has a decimal. It has no unit. No unit. This is the letter G. So A, B, C, D, E, F, G. Okay, 22 students. Students are not units, so it's not applicable. H. Okay, this is one where we really haven't talked about yet. We do have a unit. So when you're doing scientific notation, listen, when you're doing scientific notation, the number of significant digits are just in this portion of the number. How many are there? 1, 2, 3, 4. Scientific notation always has a decimal, so it's always going to be, the numbers there. For scientific notation, you always have one number before the decimal. Always only one number, but you will always have a decimal as well. So that one has only 4 sig figs. All right, this is the letter I, H-I. All right, This one has a unit, meters. Notice it does has a decimal, so I come in from the Pacific and I count 1, 2, 3. 3. That has 3 sig figs. Now I'm going to talk to you really quick before I move on. So 800 dot meters, that's 3 sig figs. 800 meters, I would come in from the Atlantic, I would go through the zeros because there's no decimal. That one has 1 sig fig. So that decimal makes a big difference in how many significant digits are there. So if you needed a 3 sig fig number out of the number 800, you could just add the decimal. All right, now there's seat practice. I want you all to try these, and you're going to enter these on Edpuzzle. I'm going to assume this is done, and so that is the end of Chapter 3B. Chapter 3C and D are in a different Edpuzzle.